going to look at a specific type of equation, what's known as the nth roots of unity. That's when z to the power of n is equal to 1, or it could be negative 1. When we find these solutions, if we were to plot them, what we're going to get is a nice regular polygon on the Argand diagram, because we know they're going to be evenly spaced. And because the modulus will be 1, because we're solving z to the power of n equals 1 or minus 1, then they must all lie on the unit circle. Let's do the fifth roots of unity. So let's solve z to the power of 5 equals 1. Now, using our de Moivre's idea, we can say, well, we know the solutions to that will be cis 2 pi k. Well, we don't necessarily have to write plus 0 there, but I've just put it there because we know that the argument of 1 would be 0. Divided by 5, we want 5 solutions. 1 is a real number, so I know they're going to be in conjugate pairs. So I'll use 0, plus or minus 1, plus or minus 2. Subbing those in, there are the 5 solutions. Well, cis 0, of course, we can work out. That's just 1. If we were to plot it, so there it is over there, cis 0 is 1. The next one's over there at 2 pi and 5. Its conjugate is also there. 4 pi and 5, its conjugate's there. And there is our lovely pentagon for that one, and it does indeed lie on the unit circle. The sorts of things they might ask us to do with these things. Here we go. We're told omega is a complex root of that equation we just solved. Wow, it's written slightly different. It's z to the power of 5 minus 1 equals 0, but it is the same equation. Show that omega squared, cubed, power of 4 and power of 5 are the other roots. Now, the important thing to note here, when they use the term complex root in this, they mean non-real. So it can't be the solution z equals 1. Because if it was, then omega squared would be 1, omega cubed would be 1, omega to the power of 4 would be 1, omega to the power of 5 would be 1, so you're not going to create the other solutions. Okay, so how do we show the other ones are? We know z to the power of 5 is equal to 1. That was the equation we were solving. Now, if omega is indeed a solution, then omega to the power of 5 must be equal to 1. Now, what we do is we play around with it a little bit. You see, omega to the power of 5 to the power of 5 would be 1 to the power of 5. And that equals 1. Well, therefore, omega to the power of 5 is a solution. Because I just substituted in omega to the power of 5 into the equation, I got the answer 1. It's a solution. Well, if I substitute omega squared in, I get omega squared to the power of 5, but using my index laws, I could rewrite that. Omega to the power of 5 squared. But omega to the power of 5 is 1, and 1 squared is 1. So yeah, when I substitute in omega squared, I get the answer 1, so it is a solution. If I substitute in omega cubed, I can do the same little idea, play around with the index laws. That becomes omega to the power of 5 cubed, and 1 cubed is 1, so yeah, omega cubed is a solution. Substitute in omega to the power of 4. Again, play around with the indices. 1 to the power of 4 is 1, therefore omega to the power of 4 is a solution. So yeah, if omega is a solution, that was the key there, omega had to be a solution, then so is omega squared, cubed, power of 4, and power of 5. So they're all the roots. Of course, there is another way of doing that which is a little bit quicker, essentially the same thing. What we do is this. Start with the equation, z to the power of 5 is equal to 1. And again, I'm starting exactly the same. Well, if omega is a solution, then we know omega to the power of 5 is equal to 1. We know that to be true. But I'm going to just play around with set notation here a bit. If k belongs to the integer, so k is any integer I like. If I substitute in omega to the power of k, well, play around with the index laws, same as I did before. I'll get omega to the power of 5 to the power of k, but omega to the power of 5 is 1, 1 to the power of k, well, 1 to the power of k is 1. Essentially exactly what I did, but now I only have to do it once, instead of doing it, how many times did I end up doing it there? 4 times. So therefore, k, remember, we defined to be an integer. So if omega is a solution, omega to the power of k, where k is an integer, is also a solution. So squared, cubed, power of 4, power of 5 are solutions. In fact, any integer would be a solution. Now some will create the same solutions. Now that we've decided these are our solutions, this is a really common sort of question. Well, show that all of these solutions add up to be 0. Now, the reason it is, if I go back to the diagram, remember our circle? If you were to add up all these vectors, place them head to tail, they will end up at the origin. So they will all sum to be 0. There's lots of different ways of proving it, by the way. Here's the first way I'm going to do it. Well, we just said these were all the roots of our polynomial. And we know the sum of the roots is minus b on a. But in our equation, b is 0. There was no coefficient of z to the power of 4. Therefore, these must all add up to be 0. There's a nice, neat way of doing it. But I really need to do something, because you'll notice my first line had omega to the power of 5, and that's not what I was asked to prove. So I need to justify, hang on a sec, you changed omega to the power of 5 to 1. How can you do that? And so that's where I remind them, now hang on, we said omega to the power of 5 was equal to 1. So I can do that. I can substitute that in. Okay. Another way of doing it. Again, there's the equation that we're starting with. Well, we know how to factorise that. It would be omega minus 1, and then in the second parentheses, it'll be 1 plus omega squared, plus omega cubed, plus omega 4. Basically all the powers going up. So remember, omega to the power of n minus 1 is always omega minus 1, and then 1 plus omega, and you just keep going up to n minus 1. Alright. So either omega minus 1 equals 0 is a solution, or 1 plus omega squared plus omega cubed plus omega 4 equals 0 is a solution. Well, I'm saying it's that one. How can I make this claim? Again, I need to justify it. Well, again, I know omega is not 1. Remember we said it was one of the complex roots. It was not the real root. So it cannot be 1. Well, if it cannot be 1, then omega minus 1 equals 0 is not a possibility. Therefore, it must be the other one. There's another way of doing it. Have a look at it. 1 plus omega squared plus omega cubed plus omega 4. That's a geometric progression. It's a nice pattern where every term is being multiplied by omega. The first term is 1. The common ratio is omega. The number of terms we've got is 5. So I could substitute into our formula that we have, and I'll end up with 1 outside omega to the power of 5 minus 1 over omega minus 1. But hang on, omega to the power of 5, that's equal to 1. And 1 minus 1 is 0, so that whole fraction equals 0. Again, I should justify why. Remember, omega to the power of 5 minus 1 is equal to 0. That is the equation we were working with. So we know the top of this fraction is equal to 0. There's 3 different ways we could solve that problem. And then they might get us to play around with them. We want to create a quadratic equation. The roots, we'll have 2 because it's quadratic. One of the roots is going to be omega plus omega to the power of 4. The other root is going to be omega squared plus omega cubed. What is the equation? Well, the sum of the 2 roots would be this. Omega plus omega to the power of 4, that was one root, plus omega squared plus omega cubed. That would be the other root. But we have just said 1 plus omega squared plus omega cubed plus omega to the power of 4 is equal to 0. Therefore, that's got to be negative 1. Let's have a look at the product of the roots. Omega plus omega to the power of 4 times omega squared plus omega cubed. Expand it all out and we get this. But I know omega to the power of 5 is equal to 1. Therefore, I could rewrite this. Omega to the power of 6 would be the same as omega. So I've divided by omega to the power of 5, which is 1. Omega to the power of 7 would be omega squared. Divide by omega to the power of 5, which is 1. And I've got that pattern again. Omega plus omega squared plus omega cubed plus omega 4, well that's negative 1. So I know the sum of the roots, I know the product of the roots, therefore there is the quadratic. X squared minus the sum of the roots, so minus 1 plus 1x plus the product of the roots, so plus negative 1, we have our equation. This one is with complex cube roots of unity. So the solution to z cubed is equal to 1 this time. We could go and prove it, but they've given it to us. They've told us it's a fact that 1 plus omega squared is equal to 0. So we don't have to go and prove it this time. What would 1 plus omega squared all cubed end up being? Okay, well, I only know two things. I know omega cubed is equal to 1 because we're talking about the cube roots of unity, and I know this other piece of information. 1 plus omega squared is equal to 0. That is all I can use. It's all I know. I have 1 plus omega squared. So I'm going to rewrite that as negative omega. If I play around with that equation, I'll get 1 plus omega squared is negative omega. Now if I cube negative omega, I get negative omega cubed. That's the other bit of information I know. Omega cubed is equal to 1. So that value is negative 1. This fraction, 1 on 1 plus omega plus 1 on 1 plus omega squared. I'm going to play around with the denominators. See, 1 plus omega I could make minus omega squared. And 1 plus omega squared I can make minus omega. It's a lot easier to play with an algebraic fraction when there's one term in the denominator than two terms in the denominator. Now put these two things together, I get minus 1 minus omega on omega squared. Let's go back to our equation. Well, minus 1 minus omega would be omega squared. So I've got omega squared on omega squared. 1. Got an answer. It's very common for the answers to these to be 1 or minus 1 because we're playing with roots of unity. A lot of times but don't assume that that's what the answer is going to be. But it is surprising how often the answer is that. We're going to form a cubic equation this time. The roots are going to be 1 plus omega, 1 plus omega squared. I know it will factorize like this. Well, they've told me 1, that's a real solution. So I've got that factorization, z minus 1. The other two would form a quadratic, so it would be z squared minus the sum of the roots. 1 plus omega plus 1 plus omega squared gives me 2 plus omega squared, plus the product of the roots. If I multiply these two things together, I'll end up with 1 plus omega squared plus omega cubed. Okay, let's tidy that up. Remember, we only know two things. Omega cubed is equal to 1. 1 plus omega squared is equal to 0. Therefore, 2 plus omega squared, well, that would be 1 plus omega squared plus another 1. So 0 plus 1 is 1. So I get minus z. 1 plus omega squared, well, that's equal to 0. Omega cubed, that's equal to 1. So we get plus 1. All right. Well, I could leave it factorised, but they've said form the cubic equation. Let's expand it out and write the whole polynomial out. And, there's a bit of tidying up to be done. And there we go. And the other thing we see a lot with these sorts of things is symmetry in the equation. Again, it doesn't have to be, but it's surprising how often it happens. So you look at those numbers, forget about the pluses and minuses, but you go 1, 2, 2, 1, nice pattern. Solve this equation. I know this. That's the second part of the factorisation of z to the power of 6 minus 1. And if you had asked me to solve z to the power of 6 minus 1 is equal to 0, that would be a much easier equation to solve because it would just have solutions. Cis 2 pi k on 6, it's a real number, so 0 plus or minus 1 plus or minus 2, I need one more, so I'll make it 3. Very easy to solve. But that's not the equation I've got. This is the equation I've got, but I can make it that. You see, if I multiply top and bottom of the fraction by z minus 1, then on the top I now have the factorisation of z to the power of 6 minus 1. Now, why can I do this? I know it's okay to do this because it's impossible for z minus 1 to equal 0. We know 0 is not a solution to this equation. Because I'd get 0 plus 0 plus 0 plus 0 plus 0 plus 1. Well, that's not equal to 0. So I know z minus 1. It would be impossible for it to equal 0. So I can put it on the bottom of the fraction. But anytime you've got a fraction equaling 0, it must be the top of the fraction that equals 0. So that's what I have to solve. Z to the power of 6 minus 1 equals 0, but z is not allowed to be 1. It's not going to be that solution. Because if it is that solution, I would have 0 on the bottom of the fraction. No good. Okay. We know the solutions to this equation. I'm just going to leave out the solution where z is equal to 1, which would be cis 0. All of the other must be the solutions to this equation. And there's 5 of them, we're expecting 5. Now these are exact value ones, so we could work these out. That's what we end up getting. A half plus root 3 on 2i, half minus root 3 on 2i, minus a half plus root 3 on 2i, minus a half minus root 3 on 2i, and negative 1 is also a solution. Quite an old HSC question now, 1996. They've told us the specific solution for omega this time. They're talking about the 9th roots of unity. Cos 2 pi on 9 plus I sine 2 pi on 9. Here's that standard sort of question again. Show that omega to the power of k, this time they've done it that way, is a solution. So anytime k is an integer, it will be a solution. Okay. Z to the power of 9 is equal to 1. We know that. So Z is equal to cis 2 pi k on 9, where k equals, you'll notice this time I haven't gone with the conjugates, it doesn't really matter, but 0, 1, 2, 3, 4, 5, 6, 7, 8, they're all integers. In other words, it's cis 2 pi on 9 to the power of k, using de Waals in reverse, and cis 2 pi on 9, that is what omega was. So yeah, Z equals omega to the power of k, where k is an integer. Remember, we could have put any integer there. Prove. There's that standard question. Written slightly different. Prove that all of these equal negative 1. Well, again, there's our equation. Z to the power of 9 minus 1 is equal to 0. I know the sum of the roots would be 0. Again, explain how you got your answer. I'm using some of the roots of this polynomial. Well, if I move that 1 to the other side, now I've got the expression that they're looking for. Ooh, hence show that these 3 things multiplied together is equal to 1/8. Now hence, that's a little trigger. Using what you just proved. What did we just prove? We just proved that all of these add up to 0. We also proved that these were solutions. Okay. I will factorise z to the power of 9 minus 1 into z minus each of those individual roots. But I've done it in a very different way, you'll notice. I've grouped pairs here. And how I've grouped them is so that the powers add up to be 9. Now, z minus 1, fair enough, is z minus 1. But then you get omega and omega to the 8 adds up to 9. 2 and 7 adds up to 9. 3 and 6 adds up to 9. 4 and 5 adds up to 9. Why did I do that? Because I know they're going to be the conjugate pairs. The conjugate pairs will have powers when we start at 0 and go up that add up to be the power, in this case 9. I couldn't fit it all on one line when I expanded this out, so this is all meant to be one line. So we have z minus 1, but then, because they're conjugate pairs, I know that we will get z squared minus the sum of the roots. Well, the sum of the roots when you're in conjugate pairs will be twice the real part. So I get twice the cos of 2 pi on 9. Then we end up with the product of the roots. Well, that's another reason putting the conjugate pairs together, because the powers add up to be 9. So when you multiply them together, you'll get omega to the power of 9, which is equal to 1, because that's the equation we were talking about. So we'll get plus 1. Then in the next one, again, z squared minus twice the sum of the roots. In this case, cos 4 pi on 9, then cos 6 pi on 9, and then cos 8 pi on 9. I can tidy that up a little bit because we have an exact value for cos 6 pi on 9. 6 pi on 9, same as 2 pi on 3. One of our exact values. So that can be done z squared plus z plus 1. It's the other 3 I don't know. Okay. I'm now going to let z equal I and substitute in. Why do that? Here's the logic behind it. Look at what we're trying to show. We're trying to show these 3 cosine multiplied together come up with something. Have a look at our parentheses. They're multiplied together. Gosh, if we didn't have that z squared plus 1, life would be so much easier. Because then I would have cos 2 pi on 9 times cos 4 pi on 9 times cos 8 pi on 9. They'd all be multiplied together. So how could I get rid of z squared plus 1? Well, if I make z equal to I. Because then I would have I squared plus 1, but I squared is negative 1. Negative 1 plus 1, 0. That was the logic behind substituting in z equals I. Let's sub it in. On the left-hand side, we get I to the power of 9 minus 1. Then we'll have I minus 1. The middle ones have now become minus 2 cos 2 pi on 9 I, minus 2 cos 4 pi on 9 I. Z squared plus z plus 1 will end up being I. And then the very last one, we end up with the minus 2 cos 8 pi on 9 I. I'm going to do some factorising here. I'm going to pull out common factors. They all have I. So I could rewrite that with minus I to the power of 4 when I take it out. So I've taken out the negatives and I've also taken out the I. And actually, I could take out those 2's out of those 3 as well, couldn't I? 2 times 2 times 2. So let's pull that out. 2 times 2 times 2 is 8. I to the power of 4 is going to be 1, so we've got minus 1, I minus 1, could I minus 1, oh, the I minus 1 will cancel with the I minus 1 on the other side. We can divide both sides by I minus 1. We've ended up with minus 1 is equal to 8 cos 2 pi on 9 cos 4 pi on 9 cos 8 pi on 9. Whew, real close but not quite there. Remember, we were trying to show cos pi on 9 times cos 2 pi on 9 times cos 4 pi on 9. So the difference is that 8 pi on 9, but 8 pi on 9. 8 pi on 9 would be in the second quadrant. The acute angle would be pi on 9. So it's the same as minus cos pi on 9. Alright, so we now have it. Because if I divide by negative 8, I end up with cos pi on 9, cos 2 pi on 9, cos 4 pi on 9 is 1/8. Ooh, quite a bit of manipulation there to get that result out. Alright, let's finish up with one from last year, a little bit more recent. Question 13c. Again, I was talking about the fifth roots of unity, but this time you'll notice it's z to the power of 5 would equal negative 1, not positive 1. First, I suppose it's a logical first part, solve it. And they're giving us a hint, in case you didn't recognise it, by finding the fifth roots of negative 1. So z to the power of 5 is equal to negative 1 this time. It will be pi plus 2 pi on k5. Again, I'm using conjugates. We'll end up with negative 1 cis plus or minus, there's the conjugates for that one, and cis plus or minus 3 pi on 5. We have our solutions. Show that if z is a solution to that, and it's not negative 1, so it's one of the complex ones, then u, which is equal to z plus its reciprocal, is a solution of this quadratic. U squared minus u minus 1 equals 0. Well, let's substitute in. We want to get the answer 0, because we want to show it's a solution. If I substitute it into u squared minus u minus 1, put it in, expand it out. Ooh, what do we got? I'm going to say that is the same as this. How can I do that? Remember, z to the power of 5 is equal to negative 1. So each of these fractions here, I can multiply by negative 1, z to the power of 5. So 1 on z squared times z to the power of 5 will become negative z cubed. And 1 on z times z to the power of 5 will become z to the power of 4. Notice it's not the sum of the roots like the other one, because you've got plus minus, but we still have to show this as 0. Remember? So how did I do it? Using z to the power of 5 is equal to negative 1. Playing around with that, I get z to the 4 minus z cubed plus z squared minus z plus 1. So I'm not going to use the sum of the roots idea. I'm going to use the factorization idea. I'm going to say, well, that's the same as this, but multiplied by z plus 1 and divided by z plus 1. That allows me to make the top z to the power of 5 plus 1, which we know is equal to 0. So we get 0. Remember, so what we've now done is u equals z plus 1 on z is indeed a solution to that quadratic. We now know that to be true. Hence, go find a value for the cos of 3 pi on 5. Let z equal cos 3 pi on 5 plus I sine 3 pi on 5. Why did I do that? Because remember, way back, we found the solutions to this equation. One of those solutions is cis 3 pi on 5. Why did I pick that particular one for z? Well, because they want me to find the cos of 3 pi and 5, so it makes sense to use that. So z's going to be cos 3 pi and 5 plus I sine 3 pi and 5. Z plus 1 on z. Okay, here's the beautiful thing. It's a number plus its reciprocal, but we're talking about roots of unity. And remember, the quick way of doing the reciprocal is the conjugate over the modulus squared. So the reciprocal in a roots of unity question is actually the conjugate. And z plus its conjugate will be twice the real part, 2 cos 3 pi and 5. Now I'm going to solve that equation, because we said if z is a solution to that original equation, then u, which is z squared plus 1 on z, will be a solution to this quadratic. Okay, so u is 1 plus or minus root 5 on 2. So from part 2, z is a solution to z to the power of 5 plus 1. We know that to be true. Then u, which is z plus 1 on z, is a solution to u squared minus u minus 1 is equal to 0. The question is, which solution is it? Is it 1 plus root 5 or 1 minus root 5? Well, let's look at cos 3 pi on 5. 3 pi on 5 is an obtuse angle, so the cosine of it will be negative. Therefore, 2 cos 3 pi on 5, z plus 1 on z, which we said is a solution, must be 1 minus root 5 on 2. That's 2 lots of it. So cos 3 pi on 5 is 1 minus root 5 over 4. There is our solution. Wow. Okay, that'll do us. So roots of unity 3C.